Right, we'll discuss about Poisson's ratio also. Okay, so let's begin with that. Let's start with Poisson's ratio. Poisson's ratio is a material property for solids. Okay. And there's a simple relationship. So basically what happens is that if we have, let's say, a cylindrical material or a cylindrical shaped solid object, whose natural length is L, and natural diameter is D. So this is the natural shape. Then on elongation of it, for example, typically it's if its length increases, then its diameter should decrease, and vice versa. Okay. So there is a relationship between the fractional change in diameter and the fractional change in length. And that one is called the Poisson's ratio. So if it is under tensile stress or longitudinal stress, so there is a relationship between how these quantities are changing. And that is called the Poisson's ratio. So we denote it with the symbol sigma. So Poisson's ratio okay. So here the quantities delta D and delta L are substituted with sign. So for example, in the above case, length expands and diameter contracts. Delta L will be positive. Delta D will be substituted as a negative quantity. Therefore, the Poisson's ratio is a positive quantity. So this Poisson's ratio is a material property. And is generally positive, which means that if delta L is positive, then delta D should be negative. And if delta L is negative, then delta D should be positive. However, the interesting thing about Poisson's ratio is that there are certain materials, both naturally occurring as well as artificially created materials, which have negative Poisson's ratio. They're very specialized materials, okay. And the artificially built ones are built for very specific purposes, like absorption of impulse during high-speed collisions, etc., or things like bulletproof vests or armor, okay, armor protection, etc. So we'll discuss about that. Make a note of this first. Yeah, graphene is correct. Then Kevlar is another example.
Sir, 1 minute.
Okay.
Yes, sir, done.
Okay, so now just I mean, this is all there is in your syllabus about Poisson's ratio, but just an interesting thing to note over here that certain materials can have negative Poisson ratio. In naturally occurring materials, it's like there are certain porous rocks. Okay. In artificially made materials, there is Kevlar that is made for that is used for making impact absorption gear like bulletproof vests, etc. So negative Poisson's ratio means that when delta L by L is positive, delta D by D is also positive. And when delta L by L is negative, delta D by D is also negative. So you might wonder how this makes sense. Okay. So very interesting way to make an analogy of that. Suppose you create a structure like this. Okay. It is made of metallic bars which are hinged together. There. Okay, so these are metallic bars which are all hinged at these places. So now if you are creating a compressive sort of force, so because of the natural elasticity of the metal, these long bars will tend to compress. But at the same time, as they compress, this structure will also tend to compress. So under the action of this, what will happen is that it should have done this. And the reverse will happen if you tend to pull it apart. Okay. So what happens in materials which have negative Poisson's ratio is that the molecular structure is such that the molecules play the role of this kind of hinged body. So this kind of mechanism is actually happening at the molecular level. Long chain molecules which behave like this. So they are useful in impact absorption. Okay, so that's just a like general knowledge factor for you people. Yeah, that too, Jagannath. Okay.
So the Kevlar, what is that?
Sorry.
Example of the Kevlar.
Yeah, Kevlar is the name of an artificially created material. You can find out about it more. Used for, like, part of its application is in armored gear, etc.
So can I do the Poisson's ratio again?
Sir,
Yeah.
sir, in this process, then the density will decrease, no?
Yeah. In compression, the density will decrease. In extension, the density will increase. That's how the volume is behaving.
Sir, when Poisson's ratio is positive, in that case also the density will change.
Yes, the density of materials do change. Okay. Under stress and strain. Okay, so this is done. So this is all about Poisson's ratio. Now, any doubts from properties of matter from your module or from HC Verma?
Sir, can you just show that note once again?
Yeah.
Done, sir.
So I have not received any request for doubts from you people. Okay.
Sir, can we send from HCV?
Yeah, HC Verma also you can send.
Sir,
Yeah.
sir, I have a doubt in a concept of proper fluid mechanics.
Yeah, tell me.
So one.
Okay, Dhruv, your doubt is from properties of matter or fluid mechanics?
So there's some properties of matter that after surface tension and viscosity that in chapter.
Okay, just can you send me the page number in the module?
Yes. 145.
Okay.
Sir,
Yeah.
sir, sir, when we were talking about the continuity equation now, in
Yeah.
that when the velocity will increase,
Mhm.
so then why the pressure decreases actually?
No, pressure doesn't necessarily decrease. That has to do with Bernoulli's equation. Continuity equation doesn't tell you anything about pressure. Continuity equation just tells you A1 V1 is equal to A2 V2. Pressure
Yes,
has to
sir.
be analyzed from Bernoulli's equation. Understood, no? Now see,
Yes.
in Bernoulli's equation, if your gravity head is constant, h is the same, then you can see that wherever the velocity head increases, pressure has to decrease. Wherever the velocity head decreases, pressure has to increase.
Sir, I was thinking in that way that if the velocity is increasing, therefore the acceleration will increase and the force will increase, therefore pressure is directly proportional to the force.
That is the logic of it. That is the logic of it. But directly it comes from Bernoulli's equation. Okay. And when you consider the force, okay, if there's a vertical section, then you'll also have to consider the vertical force, no? Because of
Yes.
gravity. So that will also come in.
Thank you.
Understood, no?
Yes, sir.
Okay. Yeah, Dhruv, do you have the page number of that in chapter
Yes,
exercise?
sir. Chapter 1 for page number is 145,
140.
sir. 145.
You mean 141?
Sir, 145.
Sir, I've
145.
sent my doubts.
Okay, okay.
Sir,
Yeah.
sir, what is the meaning of Reynolds number?
Yeah, Reynolds number is, you can just see the formula of it in your module. It is a calculation which is done to understand whether the flow of a liquid is streamlined or not. Okay.
We
If
don't
the
have.
Reynolds number exceeds a certain value, but it's not in your syllabus, you need not worry about it.
Yes.
So if the Reynolds number exceeds a certain value, then the flow becomes turbulent and we cannot apply Bernoulli's equation.
Okay, sir, because it's in one of the questions in H.C. Verma.
H.C. Verma will have it. Reynolds number is there in both in H.C. Verma as well as your module.
Sir, we don't have a critical velocity also, right?
No.
Okay, sir.
Dhruv, I'm not able to find the page 145 in my module does not have any this thing in chapter exercise.
Sir, this is the first in chapter exercise in the properties of matter liquid section.
Okay. Is it labeled as in chapter exercise 3?
No, sir, there is no written as 3, but this is the third one in the
Well,
chapter.
yeah. Okay. So it is. So there is one in chapter exercise which is there straight after elasticity, Young's modulus and all that. And
Yes.
then there is the entire theory, surface tension, viscosity. After Stokes' law, there is that in chapter exercise, no? This one. So, okay. I'll just read out the question, verify. So question 3 is this one, the rise of liquid, this one?
Question number 5.
Question number 5, okay. Which of the following is correct? A capillary is held vertically with its lower end dip, this one?
Yes, sir, the A part.
Okay. So I'm reading out the question. So it's about selecting the correct options. Okay. So in my module, actually, this is page number. So if you people have the module, in the physical copy of the module, the page number is 147. Okay. Whereas in the PDF document, it works out to be page 152. Okay. So anyhow, so I'm reading out the first option. So you have to say whether this is true or false. So in fact, let me share them. Yeah. Okay, so this is the question number 5 here. So uniform capillary is held vertically with the lower end dipped in water. Water rises to 10 centimeters. Now, if the capillary is now broken at a level of 6 centimeters, fountain will be observed. This is false. Okay. I'll explain what happens actually. Water is flowing through a capillary in a so the other options are clear, beta?
Yes, sir, the other options are clear.
Okay, so actually this can be converted into a numerical problem also. I'll explain one example of it. You might have seen a numerical problem like this also before. So suppose we have this situation, okay, that when we dip a certain capillary in a certain liquid, the natural capillary rise is a certain value, and also the contact angle is a certain value. So this is what we observe. That when we have a sufficiently long capillary, that the liquid level is not coming, the capillary rise is not bringing it anywhere close to the top. This is what we are observing. So this particular capillary is generating for this particular liquid, is generating a capillary height of h, and the contact angle is theta. So suppose given that this natural capillary height is 4 millimeters and the natural angle of contact is suppose 37 degrees. Okay. Now what we do is, now the capillary is dipped further in. Okay. So that the length of this side which is outside the liquid, that length L prime now becomes the original length minus some delta L, because you've dipped in by delta L. So that suppose becomes 3 millimeters. So it's less than the natural capillary rise. Okay. Then find the shape of the meniscus. That is the new value of the contact angle. Okay. So basically what will happen is, yes, when you dip it initially, some liquid will flow out, but it's not like liquid will be flowing out at a constant rate. So it won't act like a fountain or anything. Okay, and we'll understand why that happens. Okay. So let's go back to the basic concepts here. What happens in this case? If this point is A, just inside, and this point is B, then what is happening is that this meniscus has a radius of curvature R.
Yes.
Okay. Whereas the capillary has a natural radius, capital R, let's say. So what we saw is that the pressure at the point A is atmospheric pressure minus 2 times T divided by small r. And small r was capital R by cos theta. Remember this calculation? No?
Yes.
So pressure at the point B becomes pressure at A plus rho gh, and that should be equal to atmospheric pressure. So P naught minus 2T by R cos theta, okay, plus rho gh should be equal to P naught. And that's how we get the formula that this is 2T cos theta divided by rho r. So basically what is causing the liquid to rise in the capillary is the pressure difference that is there across a concave surface, and that concave surface is created because of that contact angle phenomena, which happens because of the adhesive and cohesive forces relationship, right? This is clear?
Yes.
Okay. Now what happens is, if I dip this thing in further, so if I dip this in further, now you can see that the liquid originally, when it is in that shape of meniscus as it was before, it's not able to create the required pressure difference. ना? यहाँ पे ये meniscus का shape अगर same है जो पहले था, but ये height अभी it's become 3 millimeters. So the pressure at this point will fall short. Na? Pressure at B will no longer be atmospheric pressure, right?
Yes.
So more liquid will have to come in like this to balance that pressure difference. So what will happen? The shape of this meniscus will now change. It will go from what it was earlier like this.
Yes, R, smaller.
So it will become ES. Actually, it will become flatter. So small r will become larger.
Yes, sir.
So that the pressure difference is becoming less. You understanding?
Yeah.
So यहाँ पे now this has changed to some r prime. Okay. So what was happening earlier was that P naught minus 2T upon R plus rho g into 4 millimeters was equal to P naught. But now what will happen is that P naught minus 2t upon r prime plus rho g into 3 millimeters will have to become equal to P naught in this case. Okay, so that means you can see that your 3 millimeters is going to be 2t upon rho g r prime, whereas here your 4 millimeters was equal to 2t upon rho g small r. So one is you can compare these two equations and you can see that r prime upon r is equal to how much? It's going to be 4/3. Okay, so that means basically cos theta upon cos theta prime is 4/3. Its contact angle will change to theta prime. So cos theta prime will become 3/4 of cos 37. In this particular case, theta prime would have changed to 53 from 37. Okay, and the radius of curvature of that top surface of the meniscus has changed by a factor of 4/3. So that's how the shape has changed. The meniscus radius of curvature increases to 3/4 of the original, sorry, to 4/3 times the original value. Okay, and the contact angle changes to 53 degrees. So as you keep pushing this further in, this meniscus will have to flatten more and more. And if you pushed it into the point where the L is tending to 0, the meniscus will become perfectly flat.
Okay.
Following, no?
Yes.
Yes.
Okay, now I'm going through other doubts also. So Durgesh has asked from HC Verma, so I'll be coming to that.
Sir, even I have my doubts from SC1.
Yeah, just send it on the text message. Okay.
I had a few doubts from the exercise.
Okay, so we will start with properties of matter, doubts from HC Verma, question number 10 and 11.
Sir,
Yes.
sir, if you don't mind, can you explain me this numerical again?
Which one?
This one, the one on the board. I couldn't find it.
Yeah.
On the
Yeah, so this is the question, okay. You're dipping the capillary further in. So as a result of that, what is happening? The meniscus shape will have to change because the natural capillary height was 4 millimeters. But now you're dipping it further in so that the length of the capillary outside is only 3 millimeters.
Okay.
So it's not able to maintain that pressure difference because that pressure at B should be equal to atmospheric pressure. No? So with the original shape of the meniscus, you needed 4 millimeters of capillary height to maintain the pressure of atmospheric pressure at the point B. Understanding that equation is written over here for that. So when you dip it further in, the shape of the meniscus has to change so that the pressure difference can be maintained. So that the pressure at the point B is again atmospheric pressure.
Yes.
So when the length of the capillary is reduced from whatever it was before, which was greater than 4 millimeter, to now 3 millimeters, this is what is happening. This is how the shape of the meniscus is changing. so that again the pressure at the point B can be equal to atmospheric pressure. So that's the second equation shown in that.
Okay.
Sir,
Yes.
sir, can you tell which lecture is what is
Which
the
lecture
lecture
is?
number? Sir, lecture
This is the
number.
final doubts and discussion lecture of properties of matter. Okay. We are actually supposed to start simple harmonic motion today, but we'll complete the doubts and discussion of this first.
Sir, actually, I want to note down the lecture number in my
Hey,
note.
why are you hung up on the lecture number? Yeah, the dates of the lectures are all there. Just figure it out for yourself. Okay, let's come to question number 10 from H.C. Verma, Properties of Matter. Okay, so it says that there's a sphere of 20 kg suspended by a metal wire of unstretched length 4 meters and diameter 1 millimeter. When in equilibrium, there's a clear gap of 2 mm between the sphere and the floor. The sphere is gently pushed aside so that the wire makes an angle theta with the vertical and is released. Find the minimum value of theta so that the sphere does not rub the floor. Young's modulus of the wire is given to you. Okay. So basically, what will happen is that originally your wire was used to suspend the sphere and the system was at rest. So the equilibrium condition was that the weight of the sphere is balanced by the tension in the
Yes, sir.
wire. Okay.
Sir, T here will be 200 Newton.
Yeah, so T will be mg, and from that you can see what is the length at which the wire will exist. So the wire won't be at natural length, it will be at some L plus delta L.
Yes, sir.
Let's say this was a tension T naught originally. And in this case, what was happening that there is a gap between the floor and this.
The wire is unstretched, sir.
Unstretched length is given to you.
Okay.
It's not saying it's unstretched. How can it be unstretched when you are suspending the weight? You understanding, no?
Yeah.
Unstretched length is that much. Okay. So what is happening here is T naught is equal to mg. So stress upon pi r square. The diameter of the wire is given to you. So from this you can see that delta L is equal to okay. This is your delta. Now, when you swing this like a pendulum, okay, so you bring it to this position theta. And you release it from here. So what will happen is by the time it comes to the vertical position, this is now got speed. So because it's got a linear speed, the tension would have increased now.
Yes, sir.
So now the tension has become T. And accordingly, this is stretched extra. Okay. Okay, now this delta L prime should be equal to delta L plus 2 millimeters in the limiting condition that is just about touching the floor. Understanding?
Yes, sir.
Yes.
So now when it's at this lowest position, T minus mg is equal to mv square upon L plus delta L prime. So T is becoming mg plus, now we can approximate this as, because obviously the fractional change is very small. Okay, as this. And then using work energy,
Half MV square mg.
V is equal to square root of 2 GL 1 minus cos theta.
Yes.
This is what the new tension has become. So the new value of delta L prime will accordingly become and this should be equal to, so you'll get this, compare this with this. All right now. So this is what we'll get from this equation. Now you might have to use binomial small angle approximation here, in which case 1 minus cos theta will be theta square by 2. Okay, so hope the question is clear.
Yes, sir.
Okay. Then let's move on to 11th question next.
Sir, sir, I have one doubt, sir.
Yeah. Tell. Okay, Piyush, you also have doubts. Objective question 7. Okay.
Sir,
Yeah.
sir, I have doubt in this question.
Yeah, tell me which question did I?
This one. Sir, delta L dash is equal to delta L plus 2 mm. Sir, it is saying that at equilibrium it is equal to 2 mm. No? Between the floor, the distance between the ball and
Yeah, so that's the above diagram. No? That's the equilibrium. When you just suspended it and it's not acting like a pendulum. Understood?
okay.
Okay, so before we come to question 11, let's go back to objective 1, question number 7. When a metal wire is stretched by a load, the fractional change in its volume equals to how much? Okay, so here see all the 3 options which are given other than none of these. That Piyush is relating to the fact that you are assuming only length is changing and diameter is not changing.
So, but the diameter will also change, no? Sir?
The diameter will change because the metal will have some value of Poisson's ratio. No?
Yeah.
So the correct answer should be D actually, none of these.
Okay, sir.
This is assuming that it does not change in diameter, which is actually incorrect, no? Because all materials have some Poisson's ratio, just like they have some Young's modulus.
Yes, sir.
Okay, then question 16 of the same thing. Okay, let's go through it. If more air is pushed into a soap bubble, the pressure in it. So what will happen if you push more air into a soap bubble?
So it should
It will tend to expand, no? Soap bubble will expand. So what about the excess pressure? 2T by R, no? So as
Yes.
R increases, what happens to the pressure? The excess pressure decreases.
Yes, sir.
So, you know, basically what happens is you tend to think that, okay, you're pushing in more air, so the pressure should increase. But that is a tendency to think that you're keeping the volume constant. If you have a constant volume chamber and you push more air, number of moles is increasing, so pressure should increase. But here the volume also increases and it overcompensates in such a way that the pressure actually decreases. Your number of moles is increasing, but your volume is increasing in by a factor which actually overcompensates to reduce the pressure.
Yes, sir.
Okay, then we have question 24. The same exercise, let's come to that. So the force of viscosity is what kind of thing in nature? Okay, so viscosity is force between molecules, no, beta?
Yes, sir.
It's an intermolecular phenomena, so it is always electromagnetic.
Yes, sir. So but then it should be nuclear, ना sir, molecules के बीच में रहेगा तो.
नहीं beta, nuclear is inside atoms, beta. Nuclear forces are what keeps the nucleus intact. You understand? So unless there is any change happening at the nuclear level, like radioactivity, etc., you're never dealing with nuclear forces.
Okay, sir. वो weak भी नहीं होगा ना?
Weak though is those forces which are for subnuclear particles. So when like baryons, etc., are collided at high velocity in particle colliders, so those kind of interactions are through the weak forces. Okay. And gravitation is only going to become significant when you're dealing with very heavy masses.
Yeah.
That is like, heavenly bodies, like all that.
Yes, sir.
Motion of a comet through a solar system, that is governed by the gravitational force. Okay. So that's that. Okay, then question 2 of objective 2. So let's come to this. So this is more than one option correct. Since the properties of a surface are different from those of the bulk liquid because the surface molecules are smaller or acquire charge due to collision from air particles or find different type of molecules in their range of influence, feel a net force in one direction. Okay. So let's understand what is the correct answer for this. Okay, so definitely the size of the molecules is not different.
Yes.
And while they do acquire charge from, this phenomena can happen, the B part thing can happen, but that's not what gives them the property of the surface. The property of the surface basically comes because of that, see, the molecules which are inside the volume of the liquid, they have liquid molecules all around them, above, below, on the side, in
So
three-dimensional.
talking about bulk liquid, no?
That is only bulk liquid, no?
Yeah.
Bulk is like within the volume, okay?
Yes.
Whereas the molecules at the surface, they are influenced by liquid molecules only below them.
Yes.
Below and tangentially from the side. Understood, no? So the way that, so this we had seen earlier, no? The property of the surface comes because of the difference in the range of the cohesive forces that surface molecules experience with respect to cohesive forces that molecules within the bulk or the volume experience, right? So that is the reason.
Yes, sir.
And because of that range of forces, they experience a net force in the downward direction, which always causes the surface to bulge a little downwards. That meniscus kind of situation. So that's why option C and D are correct. Okay. Now let's come back to the main exercise, question number 11. Okay, so
Charge curve that will not come into picture ever.
sorry, what will not come in?
So that B option, that acquire charge due to collision from air molecules, that will never come in the picture.
That does not give the properties of the surface with relation to surface tension.
Okay.
So for example, A surface will behave in the same way in terms of its surface tension, even in vacuum. No? What's the point? No? Okay, let's come to this question 11. So steel wire of natural length and area is given, is clamped between, okay. Now this load is suspended from the middle point. What would be the vertical depression? So this is just about a little bit of application of, perhaps, I mean, definitely you can use Pythagoras theorem, but maybe you will do a bit of binomial approximation also. So this is like this, that let's say that when we have no load attached, a steel wire is like this. So its natural length is L, it has a cross-sectional area A and all that. Now when we suspend some weight from the middle, it will tend to bend. So I'm showing a very exaggerated picture, but assume that actually it bends by a very small angle. So one way of saying that it bends is that it sags. Sag is the distance by which, the center point where you suspended the weight actually comes down. So this is the distance by which it has sagged. Say this is D, because we have suspended a weight. So now if we take this angle as theta, you can see that 2t sine theta is equal to mg. Okay. And okay. So now so these are your equations. Now what you can do is you can use small angle approximation. So take sine theta as approximately theta as approximately d divided by L by 2. And take L plus delta L by 2 as square root of L by 2 whole square plus d square. So now use a binomial approximation here. So use this equation, use this equation, and understood now?
Yes, sir.
Substitute sine theta in equation 1 from here, okay, and substitute delta L from this equation here. Okay, and solve these two, you'll get the answer. Okay, so this is question 11th. Just go through this once and try this out. Then we'll discuss next. We will be discussing question number 21. Okay, so finish this and go through question number 21. We'll discuss that next. Yeah, students, I had got logged out because of some internet issue. It's actually raining very heavily here. Must be it. Everywhere else also, I'm not sure. Anyhow, so let's come back to question 21. Some properties of matter. So it's to do with a barometer's construction, but also considering the fact that mercury has a negative, I mean, it has an obtuse contact angle. So let's imagine this is the cylindrical tube of the barometer. And this has been dipped into mercury. Now, negative contact angle means, I mean, obtuse contact angle means the meniscus will be like this actually. So this angle here, this angle will be 135 degrees. Okay. So if this has a radius of curvature r, it's now a concave surface, you can see. That will be related to this radius of curvature. Just a minute, people. Yeah. So now you can see that what is happening here now is that in a barometer, this is vacuum. Okay. So now this point, let's say A, is going to have a higher pressure. Pressure at, because it's on the concave side. So pressure at the point A will be pressure outside, which is vacuum, so 0, plus 2T by R. Okay. And now how we'll calculate that R? By the same method we've seen earlier.
Sir, component लेना पड़ेगा ना.
So it will become capital R upon cos 45.
Yes.
Yes.
So logic of that I'm just showing you here, but it's pretty obvious, okay, that the same type of diagram. So this time the center of curvature is inside, no?
Yes.
Not outside. So we drop a normal here. Drop a normal here. So this is the center of curvature. And this is small r.
Yes.
This is capital R. So this is a 45-degree triangle. So small r okay. So this is the pressure at the point A. So now the pressure at the point B will be equal to PA plus rho GH. So and that should be equal to pressure at the point C, which is atmospheric pressure. So the formula that we get now is that density of mercury into G into H plus 2 times surface tension of mercury divided by R root 2 should be equal to atmospheric pressure. So normally in a standard barometer, what happens is that this radius is pretty large, capital R is pretty large. So this factor is negligible. So we get that H is equal to 76 millimeter. But here if we take a thin tube, then this will come into, that will give us something which is giving a significant difference in H compared to the standard barometer. Okay, so hope this is clear. Now, unfortunately, because of the internet outage, I've lost the messages that you people sent earlier. So remaining doubts, please send me the messages again, whatever questions from HC Verma or the module. Okay, Durgesh, so we'll move on to question 29 after this. Anybody has any other doubt? Yeah, 29 is also very interesting problem. Okay, Dhruv, we will come to that also. Okay, so let's come to question 29. So in this, basically what's happening is that a wire forming a loop is dipped into a soap solution and taken out so that the film of soap solution is formed. Okay. So it's like this, that, I mean, this is that normal kind of thing that you do, that you take a wire frame and dip it into soap solution and take it out. So that wire frame now has a soap film. So let's say this is our wire frame. So after having dipped this into soap solution, you've taken it out in the air. So it's got a film of soap. So for example, if you blow into this, you can have soap bubbles. Now what you're doing is you're taking a loop of this much length. So you place like a thread, let's say, which is in the shape of a loop. So you place the thread over here. Okay. So it's got soap film both inside and outside. It just sort of gets stuck into the soap film. And then you prick a hole in the film inside this with a needle. So the moment you prick the hole, you'll observe something interesting, that now because there's only soap film outside the loop and not inside, it influences the loop in such a way that that loop will take a circular shape, take a perfectly circular shape, because inside now there's an air gap. There's soap film only outside. So surface tensional forces are acting in this way. And this loop will form a circle of radius r such that 2 pi r is equal to the circumference of that loop. Okay, so this is clear, Durgesh, why this will happen?
Yes, sir.
Okay. Now we want to do what? We have to find the tension. I think in the find the tension in the thread. Surface tension of the soap solution is given to us. Length is given. Okay. So for tension, it's that normal mechanics thing that whenever there is radial force on a circular wire or anything, you just make an FBD of a section of it. Okay. So consider a small section of this which is subtending an angle d theta at the center. So make a magnified diagram of that section. So tension is acting like this tangentially from both the sides. Okay. And surface tensional force is acting like this. So that is surface tension. So we'll take the surface tension with the symbol S over here, let's say. So we don't confuse with the tension. So it's S into R d theta. And that should be balanced by this is d theta by 2, this is d theta by 2. Okay, so this FBD is clear now?
Yes, sir.
Sir,
Yes, tell me.
nothing.
Yeah. Okay. So small angle approximation now. For this film, the soap solution. Okay, so SR d theta is approximately 2t into d theta by 2 using the small angle approximation. So T is SR d theta. But only thing is there'll be a factor of 2 over here actually. Why there'll be a factor of 2? Because remember the film has two surfaces, one above and one below. You understanding now?
Yes, sir.
Yes, sir.
And R is of course L upon 2 pi. So substitute that in there. Okay, so this question is done. So I think HC Verma doubts are done now. Or anything else pending?
We can start FHF.
Yeah, there are a couple of doubts such as Dhruv Maliwal, you have sent question number 13. I will discuss that also. A good question. It's based on that terminal velocity condition. So Dhruv, you have a doubt in all three parts or like part B or something? Okay. So what is meant by hydrostatic force beta is the buoyant force. Matlab, hydrostatic means what? The force due to hydrostatic pressure, no? And what force is exerted by a liquid due to hydrostatic pressure on a body? It is nothing but the buoyant force. So that is density of the liquid, that is glycerin, into 4 by 3 pi r cube into g. That will be your hydrostatic force. Whereas your viscous force will be 6 pi eta r into v. Okay. And when the sum of that buoyant force and viscous force becomes equal to the weight, that is when you reach the terminal velocity. So now we can complete this problem better.
Yes, sir.
You understood ना? Hydrostatic force का मतलब यहाँ पे buoyant force
Buoyant force.
और upthrust है. Okay. So rest you have understood ना? C part how to do.
हाँ, sir.
Okay. Okay. So then I think we are done with HC Verma doubts, right? So there is also one doubt from Dhruv Ladda from the module exercise 1 question number 18. So let's come to that. Yeah, this is a very nice question. Again, this will be done with that concept of pressure difference. Okay. So Dhruv, this is the question you are referring to, right?
Yes.
Okay. So glass capillary tube of radius r, water's surface tension T. Now here we'll have to use the standard value of contact angle for glass and water. This should be given in the question actually, but the standard value of contact angle is it's tending to 0. So actually, this will be like nearly a hemispherical surface like this. It will also be nearly hemispherical. Understanding? So your contact angle here is actually extremely small. It's tending to 0. So the radius of curvature of this is tending to r, which is the radius of the tube only. Okay. So if this point is A, this point is B, so pressure at the point A should be equal to atmospheric pressure minus 2T by capital R, which is the same thing as small r. Okay. And pressure at the point B should be equal to atmospheric pressure plus 2T by small r. This is on the basis of excess pressure inside a spherical surface. So from this now you can see that pressure at B minus pressure at A is 4T by R, and that should be equal to rho G L. So from that you will get L. Is this clear, Dhruv?
Yes.
So only thing in that question is that ideally this will be given to you in the exam, that contact angle. Here it's from the module, so they just expected that you use the standard value. For water and glass, it is nearly 0. Okay, so I think we are done with the doubts. So we can take an introduction into SHM today. Actually, we have half an hour of time, so let's start with our next chapter, which is simple harmonic motion. Okay. So before we get into simple harmonic motion, which is a specific type of oscillation, okay, let's first discuss a little bit of general classification of motions on the basis of periodicity. So any type of motion in physics is something where there is dynamics involved, that is something is changing with respect to time. So typically when we say motion in context of mechanics, we will say that there is displacement or velocity and all these things. But it can also be something else, like, like the state of a gas can be changing with time. So that can also be referred to as a motion, though it's not motion in the sense of, mechanics, but it is dynamical situation. Something is changing with time. So there is a dynamicality involved over there. So anyway, so now based on whether motion is periodic or not, motion can be divided into two categories. Periodic motion, which repeats itself with a definite time period, and non-periodic motion that does not repeat itself. Now, of course, typically if something is periodic, then it also involves there is some conservation principle, and therefore nothing in the universe can be perfectly periodic. Okay, not even a pendulum, not even the most accurate of digital pendulums, etc., will be perfectly periodic. There will be some loss, but assuming that we can idealize that situation. So periodic motion is something that has a definite time period. So it is repetitive, repeats in cycles of definite time period. Whereas this is the type of motion which has no periodicity.
So there is frequency.
Yes. Sorry?
Frequency involved.
Yeah, so time period means there is frequency involved, okay, because there are number of cycles per second. So okay, now further, periodic motion can be divided into two categories. This is where things get more interesting. Certain types of periodic motion are called oscillations. Okay, and others are non-oscillations. So I'll give you a very obvious example of an oscillation. The motion of any simple pendulum, it's an oscillation. Okay. Can you give me an example of a periodic motion which is not an oscillation?
So seesaw.
Rotation of Earth around Sun.
Yes, very good. Okay. Uniform circular motion or any sort of orbital motion. So for example, Earth around Sun is not even a circular orbit, it's not UCM. It is in fact more like a elliptical orbit. But orbital motion with definite time period, that's also an example of a non-oscillation. Okay. Whereas seesaw is actually an example of an oscillation only. Although it might be not a perfect oscillation because there is loss due to dissipative forces. But if we assume a perfect seesaw where there's no dissipation, so the time period remains, constant, then it is an example of an oscillation. So that brings us to the question that what is the difference between oscillation and non-oscillation? So an oscillation's technical definition is that it has a mean position, and the motion is to and fro with respect to the mean position. And in terms of physics, the mean position is nothing but a stable equilibrium position. Okay, so an oscillation is a periodic motion, okay, about or with respect to a defined mean position. So you'll see in uniform circular motion, there is no mean position. Okay, so this mean position is nothing but a stable equilibrium position. Such that there is sort of to and fro motion about the mean position. And you'll also realize that stable equilibrium means there is the action of restorative forces, which are internal conservative forces which point towards the equilibrium position. Okay, so the necessary condition in terms of mechanics is that a system can oscillate when it has a stable equilibrium position and internal conservative forces which are restorative. Only. Okay. There should be no non-conservative forces because otherwise that will damp the oscillation. Whereas in non-oscillation, there is no such thing. Another example of non-oscillation is you have a situation where a ball bounces elastically off a floor.
Crazy balls.
That continuous rubber ball is continuously bouncing up and down. So it has to and fro motion. There's no loss of energy we are assuming, so it has a definite time period, but it does not have any defined stable equilibrium position. Okay, there is no equilibrium position as such. So that's also an example of a non-oscillation. But any oscillation like a spring mass system, so you can see that it has a defined stable equilibrium position and the system has internal conservative force which is doing the job of the restorative force. So that is the necessary and sufficient condition for oscillation, that there should be stable equilibrium position first of all, and about the stable equilibrium position with respect to it, the internal conservative forces must be doing the job of the restorative force. Okay. So just make a quick note of this point, then we'll further talk about harmonic oscillation or simple harmonic motion, which is a further subcategory of oscillation. So I'm repeating here, the condition for oscillation is that you must have a system which has restorative force and stable equilibrium position. Yes.
Sir, what about the second pendulum oscillation?
Second pendulum is also an oscillation, beta, because see, their gravity is playing the role of the restorative force. Understood, na?
Yes, sir.
Any pendulum, physical pendulum, seconds pendulum, simple pendulum, okay, spring pendulum, we'll see that kind of pendulum also later. Okay, these are all examples of, okay, of course in real life they are what we call damped oscillation, because along with the restorative force there is also some drag force. Okay, but if we are able to ignore the drag force, then they are perfect oscillations.
Yes.
Just a second, guys, I'll be back. Okay, so let's come back to this. So an oscillation is any type of motion which is to and fro with respect to a mean position. Okay, so what is the mean position? Technically, in terms of physics, the mean position of an oscillation is nothing but a stable equilibrium point of the system. So for example, in a simple pendulum, the lowest point of the pendulum, okay, where mg acts in the same line as the tension, the vertical tension, that is your stable equilibrium position, because the acceleration becomes zero at that position. But when you remove the system from the stable equilibrium position, there is restorative force. So what is a stable equilibrium? That we've learned long ago in work energy. A stable equilibrium point, any equilibrium point is a point where the net force is zero. But stable equilibrium means that when you remove it from the equilibrium point, the force should be restorative. So it is also a point of local minima
Yes.
of potential energy. Okay. And net force equals to zero at equilibrium point. Okay. And the force is restorative on displacing from it.
Sir, what is
That is what.
Brahmina?
Sorry, what does?
The local. So what is that?
Local minima, beta. Local minimum. No, the potential energy is minimum at the stable equilibrium position. Remember, na, spring mass system ke liye, it's the position where your spring is at natural length. Pendulum ke liye, it is at the position at which the gravitational potential energy is minimum. So the lowest point of the pendulum. Okay, just keep these two standard examples in mind. Yes.
अगर स्टेबल इक्विलिब्रियम है तो लोकल मिनिमा की जगह पे इट विल बी ग्लोबल मिनिमा नहीं
It may be global minima, it may not be also. It really depends. Okay, we can have a system where the potential energy is actually a function like this. Okay, so, and we are making it oscillate only between this point and this point. So this is your mean position. If you give it too much energy, then it might run away. You understand it? So ऐसा भी हो सकता है ना? This is a more complicated type of oscillation. Your spring mass system will not have this kind of. Your spring mass system will be just U is equal to half kx square. No? So that is your global minima at x equal to 0.
yes
But whether it is global minima or not, it has to be a local minima. Because the important point is that your du by dx on either side has to be such that restorative force points towards the equilibrium. Remember that thing, no?
yes sir
While local maxima point of U graph is the unstable equilibrium, whereas local minima is the stable equilibrium because of the nature of the force on either side. For stable equilibrium, it is restorative. For unstable equilibrium, it is non-restorative. It takes the system further away from equilibrium. Okay. So as we do, numerical examples in this chapter, it will naturally give you a revision of the concepts of, some of the concepts of work energy, some of the concepts of dynamics. So SHM is another chapter where actually all your knowledge of mechanics will come together in solving problems. Okay. Now we come to simple harmonic motion, which is a special category of this thing, oscillation.
Sir, could you go up for a moment?
Yeah.
Done, sir.
Oh. So now let's understand a proper definition of simple harmonic motion. So you need the background of what an oscillation is, what a periodic motion is, and all that. To understand this, hence this background. So simple harmonic motion is a specific type of oscillation along a straight line such that the displacement varies with time according to a sine function. So it is an oscillation along a straight line such that the displacement varies with time sinusoidally. Okay. Now, in context of variation of time sinusoidally, the term harmonic means the same. So we say it varies sinusoidally or harmonically. A harmonic variation with time is nothing but a sine function or a sinusoidal variation with time. So actually in this term, simple stands for 1D because that's the simplest type of motion, and harmonic stands for the fact that it is sinusoidal. So in very simple terms, that if you look at the displacement from the mean position as a function of time, it should be like a sine wave. So if this is displacement versus time, where S is displacement from mean position. So that should look like a sine graph. It need not start from zero, it need not start from the extreme position, but it should be a sine curve. In that you can see that this will be one cycle or one period. So on the completion of one cycle. Okay, so displacement varies harmonically with respect to time. Capital T is the time period. So that is the terminology actually. It's called simple harmonic motion for that reason. Simple stands for the term that it is one dimensional or along a straight line. Harmonic is another term for sinusoidal. Okay. So one dimensional sinusoidal motion is nothing but an oscillation along a fixed axis, a one dimensional axis, where displacement varies with time sinusoidal. So the general equation of SHM is like this, that X or S or whatever so here I've just changed the variable from S to X, but it doesn't matter, you can keep it S also. X is the displacement from mean position. So X equal to 0 is the mean position. Okay. Here capital A, omega and phi are constants. Obviously T is time. Okay.
And A is amplitude.
Next, yeah. Next we'll discuss all these things. Omega is what we call angular frequency, capital A is the amplitude, and phi is something called the phase constant. Okay. Just make a note of this general equation first.
That's phi, right?
Sir, that is
Yes,
omega
that is
t
phi.
plus phi.
Yeah, that's phi, and this symbol is omega. Okay. This W kind of symbol is actually the Greek symbol omega. It's a bit like this. This is omega, and this is phi.
Yes.
Okay. Sometimes we use the symbol phi naught also, but phi is fine. You can use any other symbol like alpha, beta also, but this is the standard form.
Sir, what was A?
Amplitude.
Yeah, A is amplitude. We'll discuss about it. Okay, it's the maximum displacement from mean position. You can see that mod x has a maximum value of A, no? Because sine term varies between -1 and +1. So that's why it's called the amplitude. Yeah, so Harsh, to just answer your question, we can have an oscillation where the variation of x with respect to time is not a sine function, it's some other periodic function.
Sir, cos?
No, to answer your question, actually cos is not non-harmonic. Cos is also harmonic because cos is actually a sine curve. It only has a phase difference of pi by 2. So here, for example, if I take phi as pi by 2, it comes back to a sine omega t only. So similarly, even if it is sine square, it can be written in terms of sine only or cos only using the half angle formula or double angle formula. So all those things are variations of harmonic only. Okay? But we can have like a triangular waveform or a square waveform. Those would be examples. So we'll come back to those. Don't worry. So just to give you a physical example, if you have a simple pendulum, first of all, the pendulum's motion is angular. It's not along a straight line. So that itself makes it a angular oscillation and not a simple oscillation because it's not along a straight line. And secondly, if you give it too much amplitude, that means the angular displacement is more than about 5 degrees from the mean position, then the variation of its displacement is not going to be harmonic anymore. It's going to be non-harmonic. It will still be an oscillation because it still has the mean position and to and fro with respect to the mean position, but it's not going to be a harmonic one. So a good example of non-harmonic oscillation is that case only, a physical or a simple pendulum which has a large amplitude and not a small amplitude. Okay, so hope that point is also clear, Harsh. Okay.
Yes.
Now, why exactly mathematically it is the case, we will come to. Okay, we need to understand few more things before we come to that. Okay. Now let's come back to this and wind this part up. So here you can see that in this definition, capital A, it has the dimension of length. Okay. Omega has the dimension of time inverse because the quantity inside the the bracket over here should be dimensionless. Okay. And phi is also dimensionless. Or so amplitude is in meters or centimeters or whatever. Omega is in radians per second. Okay, or sometimes even radians per millisecond. And phi is in radians. So we can also see that mod x varies between 0 and A. So A is the maximum displacement from mean position. Or you can even call it the maximum distance because it's magnitude of displacement from mean position. Okay. So that is why A is called the amplitude. Now you will also see that in general, sine of theta is the same thing as sine of 2n pi plus theta. Okay. So that means sine of omega t plus phi be same as sine of omega into t plus any integer multiple of time period plus phi. So you can see that omega into n times time period is actually 2n pi. So that means the time period is 2 pi by omega, or frequency of oscillation is omega by 2 pi.
Yes, sir.
Frequency is number of oscillations per second. So omega is 2 pi into frequency. So that's why omega is called angular frequency, because it is a frequency multiplied by 2 pi, which is an angle. And finally, this is the value of x at t equal to 0. So the value of phi determines the starting point. Okay. So for example, if phi is 0, then the starting point is from mean position. If phi is pi by 2, then the starting point is from the positive amplitude, and so on and so forth. So that is why phi is called the initial phase,
Yes.
or it's also sometimes called the phase constant, because it tells you the initial position from which the oscillation is starting. Okay, so this is your basic introduction into simple harmonic motion. Okay. So what you can do is, like, if you have a bit of extra time after completing fluid mechanics, properties of matter questions and all that, and also you're doing important chapters of class 12. I don't know, you're in capacitance now or still electrostatics?
Sir, we started Gauss law yesterday.
So you're in the middle of electrostatics, so very important chapter, right? So anyway, but if you do find some extra time, you can read SHM basics from any standard textbook like Resnick Halliday or NCERT. That will help a little bit for the next lecture. So that's it for today's session, people. Thanks for attending.
Thank you,
Any
sir.
other doubts? Yeah, any other doubts from your MT or the module, etc., please send me some WhatsApp message with the question description. I'll help you out with those. Okay.
So,
Yes.
in the second line of the sine equation, what is small t in the
Second line
RHS?
of,
Down.
okay.
Like sine curly braces W.
So the thing is, like here, theta sine theta is equal to sine of theta plus 2n pi. So like that, in the time equation, if we replace the time t with time t plus some number of oscillations, so I should get the same phase, no?
Okay.
Understood the point, no? So it's like the
Yes.
same point on the graph, but shifted by n number of time periods. So now comparing above, you can see that why they are the same, because n into capital T into omega should be equivalent to 2n pi. Okay, so that the quantity inside the bracket on the right hand side is equal to the quantity on the left hand side plus 2n pi. So that means omega into nt should be equal to 2n pi.
Understood.
Clear? Okay. Okay, so we'll understand these points from the graph point of view also next time when we discuss. Okay.
Bye, sir. Have a nice.
Okay, people. Bye then. Have a nice
Thank you,
day to
sir.
you guys too. Okay.